So, good evening, everyone. My name is Shami, and I am a research scholar at the Department of Mathematics at IIT Delhi. And I will be a TA for this Sobolev space course, and we will discuss questions based on the assignments which you are going to see, which you have to solve in under the assignment section of this course. So whatever the questions I do will help you to understand the course more better. And as of now, uh, in the first week, you guys have studied about distributions. So these are the generalized functions. These are generalized functions, and why they're constructed because we want some functions to be infinite differentiables, and as they're infinite differentiable, they are like satisfy they satisfy our PD, any order PD. So they are helpful in solving, and they give a new perspective to solve PDs. And so we have introduced the distributions, and then we see how we can actually define the derivative of these distributions, and then finally we saw that we can multiply a function by a distribution and sort things like that. So our questions will be based on distributions only, some derivative of this distribution, and then some properties of distribution, and some of the things we will see that which generally we see with holds with function but are not quite holds for the distributions, and some quite interesting examples of distributions which we haven't seen in the lecture. So without further ado, let's start our tutorial session. So okay, first of all, since we know how to define the distribution derivative, the first question which I would like to do today is about the distribution Heaviside function. So what is the Heaviside function? Let me define it for you. So hx is given as h will take value 1 when my x is non-negative, and it will take value 0 when my x is negative. So it is something like this type of function which has a jump at 0. So clearly we see that this function is not differentiable. This is not even continuous at 0. But as we have seen, this is a hx is a L1 log function. So since this is L1 log function, what we can do, we can induce a distribution out of this Heaviside function. So this Heaviside function actually th is the corresponding distribution given as th of phi is equal to, it's nothing but the integral of over my r of hx and then phi x dx for all phi in my dr. So dr is the set of all CC infinity functions with having some suitable topology. So in classical sense, this is not even continuous, but as you know, distributions are infinite differentiable, so a derivative has to exist in distributional sense. So let us see what is what is the derivative of this Heaviside function. So distribution derivative I have meant. So let me write here the distribution derivative. So the distribution derivative of this function, by definition, we have defined in the sense that this is nothing but minus of th and phi dash. So we throw the derivative to the function which we are taking value. So this is nothing but th of phi dash, and so let us write it as minus integral over r of hx phi dash x dx, and this is nothing. Let's break the integral from minus infinity to 0 and then 0 to infinity, because I know that hs is constant in these two subintervals. So this is nothing but minus infinity to 0, and my hx will take value 0 there. So this is nothing but 0 times phi dash x dx, and then 0 to infinity, and it takes value 1 there. So this is nothing but minus 0 to infinity phi dash x dx. So now we can see that this is nothing but this is an indefinite integral. So how do you evaluate? We evaluate with the help of the limiting process, and this is nothing but minus limit n tending to infinity 0 to n phi dash x dx. So this is nothing minus of phi n minus phi 0 by fundamental theorem of calculus, and as we can see, and we have to also put limit, sorry, phi n minus phi 0, and when I take the limit it has to be and as I know this is phi s cc compact support, so the limit of n tending to infinity of phi n is nothing but 0 only. So this is 0 minus phi 0, which is nothing but phi 0 only. And what is phi 0? Phi 0, if you see, is nothing but the Dirac delta at phi. So this is the Dirac delta distribution. Okay, so that's how we have calculated the derivative of our Heaviside function, and this turns out to be the our Dirac delta function only. Okay, so let's proceed, and so that's how we basically see, even the classical derivative doesn't exist. The derivative exists in the distributional sense, and distributional sense this is a Dirac delta function only. Okay, I hope it's clear. Moving on. Much like now continuing. So after defining the derivative of distributions, what we have done, we have defined the order of a distribution, and as well as what we defined the support of a distribution. So to understand these things more better, let's have quotient based on the order and the support of a distribution. So let us have one quotient depend on the order and the support of a distribution. So it's again defined in the same spirit as we have support of a function. So we know the support is can be seen as the complement of the largest open set, where my function is vanishing. So with the same spirit, we define the support of a distribution. So let us have quotient based on the order and the support of a distribution. Find the order and support of the following distribution. T phi is given by -1 to 1 hx phi dash x dx. And what is hx? Where hx is the Heaviside function defined above. Okay, so let us calculate. First, so T phi is given as this -1 to 1 integral hx phi dash x dx. And moreover, what we have considered, we are considering the domain to be let us write that thing as well. For all phi in d -1 to 1. Okay, so far so good. So then we can note that one thing, that this is hx is nothing but, if we can see, so this is nothing but th. So th is the distribution generated by the Heaviside function evaluated at phi dash, right? Because with the functions phi which I'm taking is from -1 to 1 only. So, but what do I know? This is nothing but minus of th dash phi. So from our definition of a derivative, and the first case, first question, what we have seen, the derivative of Heaviside function is nothing but Dirac delta function only. So this is nothing but minus delta of phi. So this is nothing but -50. But this is nothing but only t is not, turns out to be nothing but only the Dirac delta function only. And as you know, the Dirac delta function has order 0 and support. It has a support basically singleton 0 only. So as delta has support singleton 0 and order 0, this will imply that T has support to be again singleton 0 and order to be 0. Okay, that's just using the previous question and knowing the basic fact that the delta has support on a singleton 0 and has order 0. Okay, so I hope it. Uh, so to see distributions, it's better to see the functions or distributions in some form of well-known functions, and once you are able to do that, use the knowledge of that well-known functions, and it will be easy for you to understand the easy to understand the behavior of the given distribution. Okay. Okay, so moving on. Next, we will. So now we know that we have definition distribution and all. So let us have an example. Generally, we what we try to do, we have a function, and with help of that function, we what we do, we construct a distribution, or we associate a distribution out of it. But that is not always the case. Um we'll see that an example. So let us start an example. Have an example of a not a non example of a distribution basically. So let's have one question where basic not like does defines a distribution on R. Let's see. So you can try this question if you want to. You need to pause the recording and so let us see whether this. Let us check whether it's locally integrable or not. So how do we do that? For that, what we basically do to check the local integrability of this, we consider the compact set. Let us consider k minus 1 to 1, and I have to see the integral of minus 1 to, or basically it's over the compact set k, the integral of 1 upon mod x dx. So this is nothing but, since this is an even function, this is twice of integral of 0 to 1 of 1 upon mod x dx, and this is nothing but 0 to 1 1 by x dx, but tending to 0 on the positive side. Log 1 minus log of epsilon, but this actually is not finite. and thus this is not a locally integrable function in over R. Since this is not locally integrable, this is what this implies. This implies this integral over minus infinity to infinity or over R of 1 by x phi x dx is not defined for all phi in dr. So for any since this is not locally integrable, we can construct some cutoff function or this one choose one phi function phi, which is basically phi is identically 1 on k, and phi belongs to L1 belongs to the dr. So once that is, and also I assume the phi to be non-negative, so that actually will imply that this integral of phi x divided by x over r is not finite, and once that is not finite, so we cannot define the distribution in this integral sense, and since that is not possible, this 1 by x is not actually defining the distribution, so we cannot associate a distribution to this function. So this is one. So we cannot define a distribution. So this as the answer to the question is no. Fx doesn't define a distribution. But if you see, it has the issue at point x equal to 0 only. So if I take any domain apart from any domain which doesn't contain point 0, so then that particular domain, in that particular domain, this function can generate a distribution and can be associated to a distribution. So this domain, basically the points at which I have singularities, do play a role when I am defining a distribution. So we have to be careful whenever we have functions like those which have singularities. I hope that's clear. And so let us since since we are not able to solve the since we are not able to define the distribution just 1 by x only, but our main idea is to define, eventually we want this minus infinity to infinity 1 by x phi x to be finite. So what we basically do, we there is a notion known as the Cauchy principal value, and because this function 1 by x is odd in nature, this Cauchy principal value actually turns out to be finite, and once that is the case, this actually with help of that particular thing, we are able in a position to define the distribution with help of 1 by x only. But we need something more. We, instead of considering the integral, we will consider the Cauchy principal value. So let us see what do I mean by that, and how with help with even the integral is not finite, how the property of function being odd and having the existence of Cauchy principal value help us to define a distribution with help of 1 by x as well. Okay, so let us have let me write. So let me write. So what is the Cauchy principal value? So how do I define this Cauchy principal value? So the Cauchy principal value is actually depending on the singularities of our function only. So it depends on the singularity of a function. So so in fact it's not a Cauchy, just there's the test that we actually inside this is CPV in short. So I'm defining the Cauchy principal. So this is defined dependent similarity, and then we have seen the similarity is at point x equal to 0 only. So how I'm defining as Cauchy principal value. So this is defined in the following sense. Since phi has a complex number, I can write this from my instead of minus infinity to infinity to be a minus a to a only. So the singularities of infinity are not here, and then we only have singularity at 0 only. So this will be nothing but limit epsilon tending towards 0 positive minus a to minus epsilon of pi x by x dx plus epsilon to a pi x by dx. So this is the how I'm supposed to set the Cauchy principal value, and in fact this can be written in a more compact way. Limit epsilon tending to 0 from the positive side, integral of mod x greater than equal to epsilon pi x by dx. So it's another way to write the same thing, and so that's how we define the Cauchy principal value. So what we see that this particular limit exists, and that thing exists as well, and in fact it defines the distribution as well. So first we have to show this actually is a continuous. So how defined? So this t at phi is given as nothing but the Cauchy principal value of minus infinity to infinity 1 by x pi x dx for all phi in by dr. So to show that it's a continuous linear functional, first I have to show it is actually a linear functional. So I have to show linearity first. So I consider p of lambda phi 1 plus phi 2. That will be Cauchy principal value of minus infinity to infinity 1 by x lambda phi 1 x plus phi 2 x dx, and then this is nothing but limit as mod x is greater than or equal to epsilon of integral such limit epsilon tending towards 0 on the positive side and the integral of mod x greater than or equal to epsilon. This is lambda phi 1x by x plus phi 2x by x dx. So since I'm already taking phi 1 and phi 2, we will show that this integral is finite for all phi. So let us assume for a moment that we have this t phi to be finite for all phi. So once that is the case, I know that individually this t phi 1 and t phi 2 exist. So basically individually this integral this and this exists. So I can pass the limit, and so basically I can pass the limit and break the limit to sum of limits, because I know we will show that in a moment. But assume the case to be true. Once that is the thing, we will show that this thing I can distribute the limit here. So this is the thing at limit lambda times epsilon tending to 0 from the positive side mod x is equal to epsilon phi 1x by x plus limit epsilon tending 0 from the positive side integral mod x greater than equal to epsilon phi 2x by x dx. And so then this is like I know nothing but t of, since both the limit exist I can distribute, and that will imply the whole limit is also existing. So this is nothing but t of phi 1 plus t of phi 2. So what this implies? This implies t is a linear function. So t is linear. So that actually proves the linearity. Next we have to show it is a continuous as well. So I have to show next t is continuous on this dr. So again that limit is a continuous linear function on dr. So how to show continuity? Basically, if phi n converges to 0 in dr, I have to show t of phi n also converges to 0 in 0. Basically these are real numbers only, so they converges to 0. So what is t phi n? T phi n is nothing but Cauchy principal value of let's say that I minus infinity to infinity only phi n x divided by x dx. So I have to show this particular sequence of this whole thing. This thing has to goes to 0 and then tending towards infinity. So that's what I have to show, and that we will show. So how do we show that? So we have this similarity in the denominator. So what we will try to do, we try to first I know one thing as that I know one thing as, so let us assume that phi n converges to 0. In distributions, then there exists a positive with a complex subset such that the support of my all phi n's will be contained in this minus a to a. So that is the definition of convergence in this dr. All of the supports of phi n, it has to be inside this compact set. Once that is the case, so I am actually excluding the singularities of infinity sides. That helpful. So now the Cauchy principal value of minus infinity to infinity phi n x by x dx is nothing but Cauchy principal value over minus a to a only, because all the support of ions are lying inside its minus a to a only. So now this Cauchy principal value have to deal with only the singularity, which is at a zero only. So I have to write down my Cauchy principal value. So now what I have to do, since the singularity is in the denominator, I observe one more thing. So what I do, I do one simple technique to solve this. What I do, I consider phi n x minus phi n 0 and plus phi n 0 all divided by x dx. This actually turns out to be Cauchy principal value of minus a to a phi n x minus phi n 0, provided if I were to show that both individually the Cauchy principal value of individually exists, and that will show in a moment that that exists. So let us initially evaluate these Cauchy principal values. So Cauchy principal value of minus a to a phi n 0 by x dx. So since phi n 0 is just a constant, I can take that out, and this is Cauchy principal value of minus a to a phi n 0 only, sorry, dx, or 1 by x dx only. And this is nothing but limit as epsilon tending from 0 on the positive hand side minus a2 minus epsilon of 1 by x plus epsilon 2a of 1 by x dx. Limit epsilon tending 0 on the positive hand side, and there basically the magic occurs because the CPV of this 1 by x actually exists and is nothing but log of minus a minus log of minus epsilon plus log of a minus log of epsilon. Sorry, the other thing has to be minus epsilon minus log of. So it will be phi in 0, limit epsilon tending towards 0 on the positive hand side. And since I'm actually in the log is there, I have to write a modulus inside. So this is nothing but log of epsilon minus log of a only. And this is plus log a minus log epsilon. So this is nothing but 0 only. So phi n 0, limit epsilon tending towards 0 on the positive hand side, 0. So this is nothing but 0 only. So this thing actually exists. So next I have to see how does the second integral, second CPV, whether that exists or not. CPV of minus a to a phi n x minus phi n 0 whole divided by x dx. So we have to check whether that thing exists or not. So now the why we have subtracted phi and 0. So basically this new function phi x minus phi 0 has a root at 0, and that will help us to basically help us to tackle the tackle x in the denominator. So now let us observe that. That phi n x minus phi n 0 is nothing but can be written as phi n dash psi times x minus 0 from the mean value theorem, where psi belongs to interval constructed from 0 and x, right? So what this basically implies that phi n x minus phi n 0 all divided by x is phi n dash psi, and what else we have? This is actually mod of phi n x minus phi n 0 by x. Whole thing is as the maximum of x belongs to minus a to a phi n dash x. One thing is there, and moreover, what do we have? Limit as x tending towards 0, phi n x minus phi n 0 all divided by x. So this, since this xi is lying between 0 and x, and as x is tending towards 0 only, so this xi will also will tend towards 0 only. So this is nothing but limit phi n dash 0 as x tends towards 0. This will imply that xi will also tend towards 0. And then using the quantitative phi n dash, we have this thing. And since that is the case, this will imply that the integrals sorry, that's the integrals minus a to 0 phi n x minus phi n 0 all divided by x, and 0 to a phi n x minus phi n 0 whole divided by x exists. So then that is the case, this will be where the Cauchy principal values also exist. So Cauchy principal value of minus a to a of phi n x minus phi n 0 by x is nothing but, since these integrals are existing, I have this whole thing to be equal to phi n x minus phi n 0 whole divided by x dx. Okay, so this integral is existing, so the whole thing is existing. And what do we have more? Since I know the first integral is 0 only, to show continuity, it's enough to show that the second integral goes to 0. So the mod of partial principal value of minus infinity to infinity phi n x whole divided by x dx is less than equal to minus a to a, and we have calculated the uh, modulus of this. So the first integral is something which is taking the value 0 only. The second integral, we have a bound. The bound is, we have this particular bound. So I just put the bound here only, direct itself, x belonging to minus a to a phi n dash x of dt and this is nothing but 2a maximum of x belonging to minus a to a phi n, sorry, it's modulus of phi n dash x, and as I know phi n goes to 0 in dr, this implies the maximum of this phi n dash, that thing goes to 0 as n tending to infinity. So what this basically means, this implies, and this is nothing but t at phi n goes to 0 as n tending to infinity. What this implies, that t is nothing but continuous. So finally this implies t is continuous on dr, and we have shown that it is finite as well, and this is finite, so that linearity is now valid. And so finally t is continuous dr, so this implies t is a distribution. And moreover, we have seen that this, the mod t is has to be dominated by the phi dash. So this implies that t is a distribution of, moreover, order 1, since we are able to bound it by the only the derivative thing only. So it is a distribution of order 1. So it was a bit tricky distribution. So we see that if, even though my 1 by x is there, since 1 by x is there, this Cauchy principal value help us to define the distribution, and it helps us beautifully define the distribution. So that is quite helpful whenever sometimes we're not, if we want to define a distribution, we want to do some analysis. Sometimes these type of function solutions of some PDs, but we are not able to express them as a distribution, then this Cauchy principal value help us a lot in having solution of this particular form. Okay, so that's from the this particular distribution type, and let us try to have some questioning based on the CPV of 1 by x, because this is sort of something new to us. So let's have something more on this to have more clarity on this function. Okay, so let's have some question based on the CPV of 1 by x. So let's have one more function which is quite different, and which doesn't look like a distribution, but we shows that it's again a distribution. So it's question number 6, I guess. Oh yes, 66. Oh, it's only. So the next question is whether the log of mod x defines the distribution or not. So again, this is more or less the same function as 1 by x, and we have seen that 1 by x wasn't locally integrable, so it doesn't define the distribution. So let us do the same thing for this log of mod x, whether this is a locally integrable function or not. And as we can see, it has singularity at x equal to 0 only. Basically, where our log function has a singularity. So let us check any complex set which contains point origin. So one thing which we all know that for epsilon between 0 and 1, we know that mod x epsilon log of mod x, you can see the limit as mod x tending towards 0. This limit is what? This limit is nothing but 0 only. So what this basically imply? There exists some delta positive such that mod of x epsilon log of mod x, this whole modulus is less than equal to 1 for all mod x less than equal to delta. So this definition of continuity or the definition of limit, and uh, so what this implies that mod of log of mod x less than equal to 1 upon mod x is for epsilon, and since my epsilon is lying to 0 and 1 only, so let us have integration over some minus a to a. In fact, we can have integration over minus delta over delta only, because that contains 0 only, that the origin where the singularity is there. That much is enough. Minus delta to delta dx minus delta to delta and by mod x there is no epsilon dx. So in particular, I can take epsilon to be half only, and I know this function is finite as epsilon is between 0 and 1. Since this is finite, this basically what this implies that log of mod x is L1 log r. No, that is the case. This implies log of mod x defines a distribution on R. So just to check basically the L1 locality of function, and that is there, this defines the distribution. So next, as I mentioned earlier, since we are doing CPV of 1 by x, we have to have some properties of CPV 1 by x to have better understanding of that thing. And in the week 1, we also studied that we can multiply a C infinity function by a distribution. And so we'll see some application of that thing. So both thing in a one go. So, so prove that x times CPV of 1 by x is nothing but 1 only. So it's one is basically the distribution generated by constant function 1 only. And what is this? This is C infinity function x multiplied by the distribution CPV 1 by x. And we will see that this actually turns out to be 1 only. And moreover, so to prove this, how do we go? We observe first one thing. If my phi is in distribution, this will imply that integral of minus infinity to infinity phi x dx exists. So then this thing exists. Since this thing exists, we there is no singularity or something problem in my integration. So this thing is actually nothing but equal to the CPV of minus infinity to infinity of phi x dx is nothing but equal to minus infinity to infinity of phi x dx. Okay. So first of all, let us consider CPV of 1 by x. Let us denote this thing by t only, right? So x times t of phi I start with, and how do I define my multiplication? By definition, this is nothing but t of x phi only, right? And since this is nothing but CPV of minus infinity to infinity 1 by x of x times phi x dx, and this is nothing but CPV of minus infinity to infinity phi x dx. But as we observed earlier, the CPV of minus infinity to infinity of phi x dx, where phi is from dr, is nothing but minus infinity to infinity of phi x dx, and it's nothing but 1 only. So 1 of phi, or the distribution generated by 1 of phi. So this is t1 of phi. Let me be more specific. Yes, since this holds for all phi in my dr, this implies x times CPV of 1 by x, nothing but 1 only. So basically, to have equality, we just have to evaluate at each each phi in dr, and from that we get the equality. Okay. So now what we have seen that product of a distribution and C infinity function can be defined, but that is not the case. So with the multiplication of distribution by distribution itself, so if we, even though one can define a multiplication of C infinity function distribution, but a product of two distributions is not always be well defined, is not always be the case that it turns out to be again a distribution. And this CPV 1 by x will help us to have a concrete example that shows the case that product of two distributions may not be a distribution. So let us do that problem. So this is now question number 7. The product of direct distribution delta and CPV 1 by x cannot be defined. So how do I prove this problem, or how do I solve this problem? So to prove this, we go by one addiction. So but let us suppose P is my delta and F is my CPV of 1 by x. So once if the product distribution defined, so let us suppose that Ts and St are well defined, and Ts is equal to St. So at least we want this commutativity with our functions, because since we are treating the distribution generalized functions, so this commutativity is something which is there for the normal C infinity functions. So we expect that things hold for the distribution as well, but that is not certain. That is not the case, as we'll see in a moment. So let phi to be any C infinity function. Then what do we have? We have this phi of Ts to be phi of t times s, and that is again t times alpha t times phi s. So that has to be the case if the multiplication is well defined. So we see that is not the case. So we take phi x to be x only. Then x of ts is xt times s, and which is what? X delta times cpv of 1 by x. And what is x delta? X delta is the value of x at 0 only, so it is 0. Is cpv of 1 by x, but 0 times any distribution is 0 only, that is 0. And next is xts, has it is well defined, has to begin equal to t times xs. This is delta times x of cpv of 1 by x, but we just have calculated x times cpv of 1 by x, and that turns out to be 1 only. And delta times 1 is actually delta only, is again a distribution, but again it is not equal to 0. We have a contradiction. So since this is a contradiction, we have, so product of distribution is not always well defined. So we will see what conditions we need to put to have this productive distribution to make sense, and we will see in the next week by Professor Keshavan only. So they will tell you what are the conditions we have to put to ensure that the distribution product is well defined. Okay, so finally, once the we have that notion of notion of product, you will see what other explanation you have to put to ensure this particular things to be true. We're missing out definitely something, but we will see that in the next week. Finally, to end our session, I would like to have one problem which is motivated from the following observation. We have seen that if the distribution of the derivative is 0, this will actually, we have shown in the lectures that the distribution turns out to be a constant only. So next, what I would like to see, that if I multiply a distribution by a function something like a factor 1, so that's x minus a, which has a simple 0 at a, and if that times our distribution is identically 0. So generally, when that is the case, we say that with function, instead of x minus a, with some function fx, that thing holds. This will imply that actually implies that fx is actually 0 everywhere apart from a, and the function can take any value. So with the same motivation, the same thing happens in the distribution sense, but instead of function being non-zero, we will see the function is actually a Dirac delta function. So if x minus a times t is 0, so t is not, we can't say t is non-zero at a, because that doesn't make any sense in terms of distribution. But pointwise is something which we can capture in our Dirac deltas, and that says the same thing, that t has to be of the form of Dirac delta at a only, some constant multiple of Dirac delta at a. So let us prove the following theorem, so that actually lifts the idea of uh, the same things happen in functions only. For all real a in R, x minus a t is 0 in d dash r if and only if my t is of some c times delta a for some c in r. So this is what we wanted to prove. So first of all, we prove the converse part. If my t of this c delta a, then x minus a times t is 0. So let us consider x minus a t of phi. So this is again a multiplication by singularity function, and we know how that is defined. So let us put phi in tr. This is nothing but t of x minus a phi, and what is t? T is nothing but c times delta a of x minus a phi. What is this? C of x minus a phi whole evaluated at x equal to a. But with that is the limit 0 only. So that implies x minus a t is nothing but 0. So let us do the forward part. Now what I assume that x minus a times t is 0, then I have to show that t has the following form: t times delta a or some c naught. So first of all, let us observe what our assumption implies. So for find dr, we have x minus a t of phi to be 0. That means t of x minus a of phi to be 0. So basically t is vanishing all those functions psi which has the following form: x minus a times phi, where my phi is in dr. So let us take chi to be in dr, and what our idea is to break the function into two parts, such that one part is something which have a 0 at a, and another which is the remaining residue part. So generally when that we try to do, we do in a such a way that chi x minus chi a plus chi a, so that is the easiest break up our function. But this is not a uh, dr function, so this doesn't have a compact support. We have to do, but we have to so this particular break uh, this is a 0 at x equal to a, and but this break, the way in which I'm breaking my functions into two functions, is not a very good way, because this another function is not a CC, is not a CC infinity function, and it's not a DR function. So what we have to do, we have to break in a way so that idea will be the same, but the function, the second function I have to consider is again is in DR. For that, what we can do, we can choose theta in dr such that theta of a is 1. So this is something which I can choose and a fixed. So this is fixed now. So if I consider chi of x minus chi of a times theta x, right? If I consider this thing has a 0 now at x equal to a, because theta is a is 1. So if I take this to be my psi, so this will belong to dr only. And not only that, moreover, chi x is nothing but uh, chi a theta x plus psi x. And what do I have? Psi a is nothing but 0, right? So let us evaluate this t at chi only. T at chi only is nothing but t at chi a theta plus psi, but t is linear. So this is chi a times t theta plus t psi. But now since know that the psi has a 0 at x equal to a, this thing all vanishes to 0. This is nothing but chi a times t theta only. And since theta is chosen to be a fixed function dr, which is independent of chi, but theta is independent of chi, so let this to be c equal to t theta. Then t chi is nothing but delta a of chi times c, which is nothing but c delta a chi, which we wanted to prove. So that's how this is. Then that holds for all chi in dr, and thus this proves that all of my so eventually this implies that t is nothing but c times delta a only. So this finally proves that t is nothing but of this some constant multiple of Dirac delta at a. So that's how you prove that this thing. And with this, I end my session today. So I hope we have lifted some of the properties of functions to the generalized functions, and many properties are holding very beautifully. Some properties are not, so we need to see what extra assumptions we have to put and what exactly are missing out there. That we will see in the next week. And finally, I would say try more questions on distribution that will make this topic more clearer to you. And with that, thank you.